All right, we're rolling in action.
Okay, my name is Mauricio Terrones. I'm from Penn State University, from the physics department, and also associated with the chemistry and material sciences. And my work that I was presenting this time was related to the role of defects in transition metal dichalcogenides. So the role of defects in monolayers, basically, that's what I was discussing. And we want to tailor the properties of these materials just by introducing in a controlled way different types of defects. So I discussed the different functionalities of defects according to their dimension. So you can have zero-dimensional defects like vacancies or add atoms or dopants, and you can have one-dimensional defects like edges or interfaces or grain boundaries. And then you can have two-dimensional defects in these systems, which happen when you stack layers of different systems, or you fold these sheets, or you wrap around these sheets on the surfaces, and then it becomes sort of bumpy surfaces. So all these defects will then introduce new properties. For instance, some of the things that I was discussing, it was if you introduce dopants and you control the dopant levels, you can also change the, for instance, ferromagnetic properties of the material. At some point, you can even observe ferromagnetism from a semiconductor, from these monolayers that are semiconductors, if you dope it or you introduce vanadium, for instance. There are other cases where you can use defects in order to see other electronic properties changes. So when you introduce dopants like carbon, hydrogen, or like vanadium again, you can change the transport from an N-type transport, for instance in tungsten disulfide, to an unbipolar transport system. So these changes are dramatic, and they are only influenced by a few concentrations or a few amounts of other foreign elements, which we call defects. There are many ideas of what is next related to these defects in monolayer systems of TMDs. And I think I just gave a brief overview of the potential of introducing defects and how these defects can change electronic and magnetic and optical properties as well. And of course, at the end of my discussion, I also talked about what is the effect of having these monolayers on cells, especially in particular of cells, cancer cells. So can you use these systems because they are fluorescent, right? So they fluoresce. So can they be used as biomarkers? And this is something that I showed with some of the research we're conducting. It's that cells start ingesting these materials. These are monolayers. And when they ingest these materials and you shine or in a fluorescence microscope, you start to see that the cells start shining, right? So they fluoresce because they have ingested this fluorescent material. And so these materials can be used as biomarkers. I think the impact of this is that if the cells can be observed or be tracked with these biomarkers, new type of biomarkers based on fluorescent two-dimensional materials, it has the implication that as the cells reproduce into first generation, second generation, third generation, you can still track the cells even for later generations. And then you can track evolution of the cells, and you can track, for instance, infections as well. So there are different implications of this data. If you can, for instance, internalize these fluorescent systems with fluorescent, these tiny crystals of these monolayers into viruses, and if they are inside the viruses, you can basically monitor how the viruses and how infections happened in different cells. So there are some implications about this, and of course, the latest thing would be, can you use these materials for imaging or to do tomographies of three-dimensional tomographies of cells or other tissues. And I think that's still an open question, but that's the latest sort of possible applications that I showed related to the biology. But in general, so I discussed different types of defects in these two-dimensional systems and all the implications and how you can control. The challenge now is really to control the type of defect, the amounts of defect, so you can control the properties at will. But I think that's work for the future workshop or for some other people. Thank you.